In today's lecture, we will learn about primality testing. Our objective is the following. So, design an algorithm, a randomized algorithm, such that first it should run in polynomial time, that means if the input is of size, let us say k, then the algorithm should take no more than k raised to alpha steps. For some fixed alpha. The second requirement is for every prime the algorithm should output prime and for every composite number the algorithm should output composite with probability greater than half. Okay. So, this probability is over the random choices that the algorithm makes, and this should be true for every composite number. Okay, so, we will use some elementary principles from group theory. Okay, so, let us initially understand what is a group. So, a group is a collection of mathematical objects. You can call it as a set with a binary operation. Let us say we call it a star, okay, such that first star is associative, so since it is a binary operation, we will assume closure. It is for any two elements in the set. If you combine them using star, the resultant element will be an element of the group. Second, there exists an element E or identity such that for every x belonging to G, x star E is equal to E star x. And the third requirement is for every element there exists an inverse, that is there is an element y such that x y is equal to identity, okay, and that is equal to y times x as well. Okay. So, if binary operation which has these three properties is essentially called as called a group. So, you can think of groups as mathematical structures wherein you can multiply and divide. Okay. So, if you call the operation as multiplication, you can call it by whatever name, you can call it addition, multiplication, whatever is the binary operation, you can essentially multiply and divide. Okay. That inverse operation you can perform. Okay. So, let us see an example, the example that we would require. So, this will be called as ZP. So, let us say P is a prime number, and if you look at numbers 1, 2 up to p minus 1. Okay. So, let us say if p equals 7, then this will be these numbers from 1 to 6. Of course, if you add 5 and 6, you will get 11, but that is not one of the elements of ZP. Okay. But here the operation we are going to redefine it. So, we will have mod 7 multiplication. Okay. So, we can just represent this entire thing by a table. Okay, so 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 are the elements. 1 into 1, that will be 1, so mod 7 as well. So, this is a special group which has an additional property of commutativity. Okay. So, we will say that a group is commutative if A star B is equal to B star A. Okay. The order does not really matter. 2 into 2 is 4, 2 into 3 is 6, 2 into 4 is 8, which is 1, 2 into 5 is 10, which is 3 mod 7, this is 5. So, you can just fill up the elements of this group, 3, 4 is 12, 5. Okay. So, this will be the multiplication table for this particular group. Since it is under multiplication, we will just write it as Z star P. Okay. Now, you can see that this particular operation has many nice properties. Each row is a permutation of 1 to 6. Okay. And we can take this operation and do multiplication as well as division. That is, if you have, let us say, A times B is equal to A times C, we can write, we can basically apply cancellation. So, this would imply that A equals C, sorry. This would imply that B equals C, because we can just multiply both the sides with A inverse. So, inverse times A times B, this is equal to A inverse times A times C. So, this gives you identity, this gives you identity, identity times anything is going to be identity. So, from all these rules we can conclude that B must be equal to C. So, we can basically do cancellation. Okay. So, that is a group, and ZP star. So, there is a theorem, ZP star is a cyclic group for every prime number. Okay. For example, if you, so cyclic group means it can be obtained by taking some particular element and multiplying with itself. So, here if you take the number, so let us try, if you take the number 3 square is 9, that is 2, So, let us compute 3 square, 3 cube, 3 raised to 4, 3 raised to 5 and 3 raised to 6. This is equal to 3, this is equal to 9, which is equal to 2, and this is 2 into 3, that is going to be 6, and this is going to be equal to 6 into 3, that is 18, that is 4, 12, this is equal to 5, and 5 into 3 is 15, which is equal to 1. So, you can see that the entire group, all the elements in the group were generated. So, Z star 7 was generated by 3. So, therefore, Z star 7 is a cyclic group. Okay. So, this is not in general true for an arbitrary group, but for every group which has which is obtained from a prime number in this format is going to be a cyclic group. Okay. So, this is a theorem that we will need. And we will also require a couple of other theorems. The next theorem that we will use is called Logons Theorem. Okay, so, this states that, so suppose this is a group and let us say this is a subgroup. Okay. A subgroup is a, you need to define what is a subgroup. So, subgroup is a subset of G such that that subset is a group in its own right under the same operation. Let us say G was a group under star. If you find a subset which is a group under the operation star, that will be a subgroup. So, if you look at this group Z star 7, and if you take the numbers, let us say 1 and 6, okay, you can verify that this is going to be a subgroup of Z star 7. So, Lagrange theorem says that the order of the group divides the order of the order of the subgroup divides the order of the group. Okay, which essentially means, so if G had 35 elements, then any subgroup must have either one element or 5 or 7 or 35 elements. Okay. These subgroups are essentially these are called the trivial subgroups. Because 35 element subgroup is the group itself, and the single element subgroup is going to be the group which consists of just identity elements. So, these are non-trivial subgroups. Okay. So, these are the theorems that we would require, and there are some additional results that we would need, but we will derive them on the fly. Okay. So, now let us look at primality. Okay. So, we were given a number n. Okay. We will assume few things about n. First, we can assume that n is odd, and next we will assume that n is not a prime power, that is, it is not of the form p power okay. So, we will assume that p is not, n is not a not of the form a to the power b. This can be easily checked, okay, for any input. Is it of the form a to the power b? This can be checked in polynomial time, deterministic polynomial time. Okay, so once we have completed these checks for the input, we can assume that n is odd and n is not of the form a to the power b. In particular, n is not a prime power. Okay, and our algorithm, the steps of the algorithm are as follows. So, choose a random a from 2 to n minus 1. So, compute R such that R satisfies the following condition. N minus 1 should be equal to 2 power s times r, and r is an odd number. So, notice that this can be done only in one particular way. For any number, you just take out all the powers, all the powers of 2 from it, and whatever remains, that is what we call as r. Okay. And this can of course be done in polynomial time, and since n is an odd number, n minus 1 is going to be an even number. So, r certainly is less than n minus 1, and then we will compute the following terms. So, we will first compute a to the r, and then a to the 2r, a to the 4r, all the way up to a to the. So, we keep on repeatedly squaring the numbers that we have obtained. These are all a to the r squared will give a to the 2r, and that squared will give a to the 4r, and then finally we will get a to the 2 to the s times r. Okay. Now, a to the 2 to the s times r should be equal to 1. Okay, why so? Well, it depends on whether n is prime or not. So, we will compute these, and then based on the values that we have obtained here, so these values we will look at it more carefully, and based on these values we will conclude whether the number is prime or composite. Okay. So, if a to the 2 to the s times r is not equal to 1, we will output composite. Okay. So, if that is not so, else if, so in that case a to the 2 to the s r is going to be equal to 1. So, if the last term is going to be 1 in the other cases. Okay. Maybe there are ones before that, okay, but there is a last stage at which, last position at which a number which is not 1 when squared gave you 1. Look at that position. Okay. So, that position let us call it as t. So, we will say else we will determine the index at which the last one appears. Okay, so let us call this as the index I, and if the I minus first position is not equal to minus 1. So, minus 1 here means the number p minus 1. So, these squaring operations we are carrying that out in mod n. Okay. All these operations we are carrying out mod n, and if the I minus first position is not equal to minus 1, so minus 1 is the equivalent of p minus 1. So, p minus 1 mod p, we can just write it as minus 1, or minus 1 as a symbol for p minus 1. Okay. And notice that minus 1 squared is essentially p minus 1 the whole square. You can verify that that is going to be 1 mod p. Okay. So, if this is the case, if this is not equal to minus 1, then we will declare composite, and otherwise declare prime. So, otherwise output prime. So, this is our algorithm. Okay. So, there are two places where the algorithm outputs composite, and if it does not output composite, the output is going to be prime. So, now we need to argue that this algorithm has the correctness requirements that we had initially mentioned. Clearly, the algorithm runs in polynomial time, okay, because all these calculations, this is s repeated squarings and s is okay. So, s is less than, let us say, log n. So, when we talk about polynomial time, we want to mention that the algorithm works in polynomial time. So, if the input size is x, then the algorithm works in x to the power alpha. At most, it does not take more than x to the power alpha for any input of size x. Okay. So, here if an n bit binary string is being given or an n bit decimal number is given, the input size is log n, okay, and so we want the algorithm's running time to be log n to the k for some fixed k. Okay. So, here all these operations, s is at most log n. So, we have only log n multiplications, and each the numbers involved are between 1 and log n, between or 0 and log n. So, all those operations can be carried out in polynomial time. Now, let us look at the cases where it is declaring the number as composite. Okay. First is when a to the 2 to the s are not equal to 1. Okay. So, we will write this as a lemma. If a to the 2 to the s times r is not equal to 1 mod p or mod n, then the number n is not prime. Okay, why is this so? Well, we define the set z star p consisting of all elements from 1 to p minus 1. We could also write the set z star n minus 1 or n for an arbitrary number n, which consists of all x such that x less than n and GCD x n is equal to 1. So, take all the numbers which are relatively prime to a number and collect them in a basket and allow the multiplication operation to be mod n multiplication. You can check that that will indeed form a group. For example, if you take z star 15, this will consist of the following elements 1, 2, 4, 7, 8, 11, 13 and 14. So, there are 8 elements here, and you can verify that this collection forms a group under mod n multiplication. Okay. So, z star n is always a group. So, you can do the operations there, but note that if n is prime, then z star n has n minus 1 elements, and if n is not prime, then z star n has less than n minus 1 elements. In fact, the number of elements there will be given by the Euler-Toshen function. Okay. So, whenever n is prime, this group has n minus 1 elements, and otherwise it has less than n minus 1 elements. And we can show that if you take any group, any finite group G, and you take any element a to the number of elements. So, we will denote it by order G, this is going to be equal to 1. Okay. Why is this so? We will just show this for commutative groups. R group is anyway commutative. So, take all these elements 1, 2 up to p minus 1. Okay. Now, when you multiply this with an arbitrary element, let us say x, okay, you will get x times 1, x times 2, x times p minus 1. Okay. Now, this collection as a set is going to be exactly equal to G. This is anyway equal to G, and this is also going to be G, because all these products are going to give you distinct elements. That is, x times y1 is equal to x times y2 implies y1 equals y2. We can apply cancellation. Okay. So, if you take distinct elements y1 and y2, you will get distinct products x y1 and x y2. Okay. So, there are going to be p minus 1 elements here, all of them being distinct. So, that has to be exactly the group G. So, we can write 1. So, if you take the product of all the elements 1, 2 up to p minus 1, that is going to be equal to x times 1 times x times 2 times x times p minus 1. Okay. So, now you can just cancel off things, you can rearrange. So, this if you write it as p minus 1 factorial, this is going to be equal to x raised to p minus 1 times p minus 1 factorial. All these operations carried out mod p minus 1 or mod n. Okay. So, these gets cancelled. So, we will get x raised to p minus 1 is equal to 1 mod p. Okay. This is also known as, so this result when applied to Zp star is also known as Fermat's little theorem. Okay. So, what we know is when the number is prime, it has to be the case that x raised to p minus 1 should be equal to 1. So, if it is not 1, then we can readily declare it as composite. Okay. And 2 raised to s times r is nothing but n minus 1. Okay. So, if this is not equal to 1, then the number is not prime, and therefore, we are correctly declaring it as composite. Now, let us look at the second instance where we are declaring it as composite. We checked at the last index from where there was from where the sequence of ones had begun. Okay. One before that index, if a number other than 1 appears, other than minus 1 appears, then we had declared it as composite. Okay. So, let us look at this more carefully. So, we had computed a raised to r, a raised to 2r, a raised to 4r, and let us say a raised to 2 to the I r, and then a raised to 2 to the I plus 1 r, all the way up to a raised to 2 to the s r. This has to be 1, and if a 1 appears at any place, its square is also going to remain as 1. Of course, if a minus 1 appears at some place, at the next place the minus 1 squared is going to give you 1. So, if you look at the last one, the position before it could be either a minus 1 or it could be something else as well. Okay. If it is some other number, okay, let us say this 3, then we would have declared it as composite. Okay. Why is this a correct thing to do? Okay. So, these will be what we will refer to as non-trivial square roots of unity or square roots of unity. Okay. So, if you look at the equation x square equals 1, this is precisely 2 roots when we are talking about real numbers, plus 1 and minus 1. Okay. We could in a general, in an algebraic structure known as a field, we could look at the equation x square equals identity. Okay. And or so in this case, if it is a field, there can be precisely 2 roots, okay, plus 1 and minus 1. So, here we have a case of, we need to first show that the algebraic structure that we are working with is indeed a field, and then what we have essentially found is a non-trivial square root of unity. And if the algebraic structure that we were working with happens to be derived from a prime number, that is going to be a field, and for non-primes it is not going to be a field. Okay. So, that is the essential idea behind why we are declaring the number to be composite when we see a non-trivial square root of unity. So, let us try and prove this using more simple number theoretic arguments. So, let us just look at this equation. So, we will define what is called as a quadratic residue. Okay. So, if A is equal to x square mod n, okay, then we will say that A is a quadratic residue. Okay. So, if you take for example n equals 10, okay, and if you take the number 5, 5 is a quadratic residue. So, 5 is a quadratic residue as, let us say 5 is equal to 25 mod 10, okay, and this is a square. It so happens that it is a square of 5 itself, but let us say if we had taken n equals, let us say 9, okay, and in that case we can say that 7 equals 25 mod 9, therefore 7 is a quadratic residue. Okay. So, any number which you obtain by taking the remainder, when you divide a square, that is, take a number, multiply it with itself, whatever in the group, and compute the remainder mod n, the number that you get is what is called as a quadratic residue. So, this is a claim. exactly half okay, so we will prove the following statement. So, A equals, let us say, alpha to the power k mod n is a quadratic residue if and only if k is even. Okay. So, here I am assuming that alpha is a generator of, let us say, Z p. Okay. So, we are looking at the group consisting of 1 to p minus 1, and in this particular group, let us say alpha is a generator, and we are looking at all numbers of the. So, since alpha is a generator, the different elements will be alpha, alpha square, alpha raised to p minus 1. P being an odd prime, it is going to be I mean p minus 1 is going to be an even number. So, here we are saying that all these quantities, okay, I mean these quantities are going to be quadratic residues. Okay. Well, one thing is clear, these will be quadratic residues because they are alpha raised to some 2 to the power 2 times k, which can be written as alpha raised to k the whole square. So, when you go mod n, whatever you get, that is by definition a quadratic residue. But what we want to argue is that these alone are quadratic residues and there are no other quadratic residues. Okay. How do we say that? So, suppose not, okay. That means alpha to the, let us say, I mean 2 t plus 1 for some t is a quadratic residue. Therefore, I mean, so let us say this is equal to A, we can write this as alpha 2 t plus 1 mod n, which is equal, so A I mean whatever is your A is equal to alpha raised to 2 t plus 1 mod n, that is a perfect square, right. I mean this alpha 2 t plus 1 is a perfect square. So, that is some beta raised to 2 k. Okay. All these, so we will not write mod n because all these things are carried out in mod n. So, b to the, so A can be written as b to the 2 k, and since it is beta to the power 2 k, we can write, since this is a cyclic group, beta itself is going to be alpha to, let us say, some power r times 2 k. Therefore, we can write alpha to the 2 t plus 1 is equal to alpha to the 2 r k. Now, this implies that alpha to the 2 t minus, so 2 t plus 1 minus 2 r k is equal to identity. This would imply that alpha to the 2 t plus 1 2 times t minus r k plus 1 is equal to identity. Okay. But if alpha to the to some power is identity, okay, the smallest number which has this property, that alpha to the, let us say, capital T is equal to identity, means T should be a multiple of p minus 1. If it is anything smaller than p minus 1, that means alpha does not generate, I mean alpha does not generate the entire group. And if it is something which is not a multiple, then we can take the remainder of, I mean let us say alpha to the t equals 1, take t mod p minus 1, okay, alpha. So, let us call this as t prime, alpha to the t prime will also be equal to 1. Okay. So, we can say that this number 2 t minus r k plus 1 should be a multiple of p minus 1. Any multiple of p minus 1 is an even number, but this is an odd number. So, this is not just possible. Okay, so, we can just write this down as the following: 2 times t minus r k plus 1 should be a multiple of p minus 1 and thus an even number. Okay. So, that will give us the required contradiction. Okay. So, every quadratic, so we can say that if it is if any number is a quadratic residue, then alpha to the k, that k should be even, and this would also mean that the square roots of a, so we can write this as an observation. So, by square roots of a we mean those numbers which when squared modulo n gives a are going to be alpha to the power 2j. Okay. So, we can write the square roots as alpha to the j and alpha to the j plus p minus 1 by 2. Okay. So, you can think of this mod p. Okay. P being an even odd number, p minus 1 by 2 is going to be an integer, that plus j. So, alpha j square 2j, if you square it you will get a, and if you square alpha to the power j plus p minus 1 by 2, there also you will get alpha to the 2j times alpha to the p minus 1, alpha to the p minus 1 is going to be 1, this is going to be a. So, these are going to be the square root, and there cannot be any other square root, because you can say that if there was any other square root alpha to the power I, okay, then we will get, so let us see what goes wrong. If alpha to the I is a square root of a, then alpha to the j, so alpha to the 2j is equal to alpha to the 2i. Okay. And since these are equal, we can conclude that alpha to the 2 times j minus I should be equal to identity. Okay, it should be equal to 1, and therefore, j minus 1. So, what are the possibilities? So, j minus I should either be 0, okay, or j minus I should be equal to p minus 1. Okay, if j minus I equals p minus, sorry, j minus I should be p minus 1 by 2, only then 2 times j minus I will be equal to p minus 1. This cannot be any other multiple, because 2 times j minus 1 cannot be as large as j minus I is at most as big as p minus 1. It is going to be definitely smaller than p minus 1. Therefore, 2 times p minus 1 cannot be larger than p minus 1. Therefore, we can conclude that 2 times j minus I must be equal to p minus 1, and this would tell us that I is going to be equal to j, yeah. So, j plus p minus 1 or j minus p minus 1 does not really matter mod p. Okay. So, this will tell us that j minus I is equal to p minus 1 by 2, or j is equal to p minus I by 2 plus I. Okay. So, there are only 2 possibilities essentially. So, you can have precisely, if p was a prime number, it can have at most 2 roots of unity, and we know that those roots, it can, any number can have at most 2 roots. So, if p is a prime number, then any element A can have at most 2 roots. Okay. So, in particular if you take the element 1, it can have only 2 roots, 1 and -1, because these are anywhere roots, it cannot have any additional roots. When we find a number which satisfies this condition, that is it is a non-trivial square root of unity, then we can declare it as composite. Okay. So, what we have concluded is the following: whenever this algorithm declares the number as composite, there is a sound reason. I mean, it is never incorrect on that count. Okay. It is always correctly declaring the number as composite whenever it declares it as composite. Okay. It does not make a mistake in that. Whereas, whenever it declares a number as prime, things could go wrong. Okay. We will check with what probability things could go wrong. Okay. So, let me just summarize whatever we have done so far. So, we have an algorithm with the following properties. First, for all primes, the algorithm would return the correct answer. This is because what we had argued is that for every composite number, I mean whenever the algorithm declares a number as composite, it is never a prime number. Okay. So, that would essentially mean that whenever the algorithm declares the answer as whenever the algorithm gets an input as a prime number, it cannot declare that as composite, and hence for all primes the algorithm must return the correct answer. The second thing that we have, that our algorithm we have checked is the algorithm runs in polynomial time. What we need to verify is that for every composite there exists a significantly high probability, this we have not showed yet, probability that the algorithm returns composite or outputs composite. Okay, so let us see what happens for a composite number. Okay, so we had randomly chosen a number from 2 to n minus 1. Okay. So, the numbers which will the choices of A which will result in the number being declared as composite, we will try to bound that set. What we will show is these A's which will make the number a composite number, or the A's which will bear testimony to the compositeness of the number n will essentially be a significant collection of means significant subset of 2 to n minus 1. To show this, what we will indeed prove is the numbers which do not which bear false testimony will essentially form a group. It will form a strict subgroup of the set Zn star. Okay. Since it is a subgroup of Zn star, its size is surely less than half of the size of the total elements in Zn star. So, that will surely be less than n by 2, okay, and I mean that is by Logons theorem, and that will basically conclude our proof, and that is the part we will do in the next class.